Okay, let's start. It's a new tripod, it's weird. So we're moving on to another section, but before we do, I just want to mention a couple consequences of Green's theorem. And then we'll move on to 13.5 and talk about curl and divergence. Two new mathematical operations. By the way, what does Green's theorem say?
So, Green's theorem said that if you have a function p of x plus q of y, no?
No.
P of x minus, no, p of y minus q of x, and then you do a double integral.
Oh, so you're telling me the double integral. Okay.
Mm-hmm.
So there's a double integral.
And q of x.
Of what?
Q respect to the
y. The partial of q with respect to x.
And then minus p y and then the
equal to the closed
and then equal to the single integral of p
px.
px.
Right, so p is a function of x and y.
And then q dy. Exactly. It's hard to say.
Okay. Tell me about these symbols. What do we know about p and q?
They're both functions of x and y.
Functions of x and y. What are their requirements?
It has to be conservative. No?
It's possible oriented. They have to have a first.
Well, that's something on C. The functions can't be oriented.
Have to be differentiable.
They're differentiable, of course, but there's a further condition.
C has to be a closed curve, to simple closed region.
I'm talking about p and q, the functions. So these are functions defined on V with continuous first order partials. So not only do these guys have to be continuous on the region, but their derivatives also have to be continuous on the region, or this equation is frankly not true. What about C? What is C?
I have a question.
Yeah.
So saying that they have continuous first order partial would be equivalent to saying this is smooth. The smooth is implied continuous first order partial.
You can kind of say the vector function that gives the normal vector to the surface they form is smooth.
Okay.
There's another level. We'll talk about normal vectors in a bit, but it's not exactly as saying they're smooth. Remember, our definition of smooth was in terms of vectors. So p and q here are not vectors. They're scalar functions, but they must have continuous first order partials on D. What do I know about C?
It's a closed piecewise smooth curve.
Yeah?
And it's also the boundary of D.
So it's the boundary of D, that's the important part. It's the boundary of D, and it's piecewise smooth. And closed. And what is D? It's an open, simply connected region. Now you may see problems in your textbook. I'm not sure if in the online homework there are problems like this. But in the textbook there's a problem where it shows you an example of where this equation failed. And it asks you, does that mean Green's theorem is wrong? But the answer was no, it's one of these things that messed up. So these things have to be in place for this equation to hold. Okay? So that was Green's theorem. Now let's look at some consequences here. We know another way to say this. Is to say that, this is kind of memorized backwards. Usually it's memorized the other way, but let me just continue with this pattern here. you can think of the right side as a work integral, right? Where your function f is the vector function with components p and q. And if you multiply this out, you kind of get the right side. And so this means, let's assume that f is conservative. By the way, tell me what it means for f to be conservative.
Doesn't it mean that the partial of q with respect to x and the partial of p with respect to y are the same?
Right, in 2 dimensions, yes. So that means the partial of p with respect to y is equal to the partial of q with respect to x when f is 2D. What does it mean in general?
It needs to have a potential function.
It has a potential function. It means that there exists some scalar function f such that the gradient of f is equal to that guy, right? But a consequence of that, you can actually flush it out. Just by taking partial derivatives and applying Perros Theorem, you can prove that this equation has to hold if it's a 2-dimensional function. Okay, so that's true. So what would that actually...
What do you say about Perros Theorem? You just mentioned like...
Oh, Perros Theorem is a theorem that says if your partial derivatives are continuous, then it doesn't matter what order you take partial derivatives in. So basically, so as long as all your derivatives are continuous, the order in which you differentiate, take a sequence of partial derivatives, it doesn't matter. So if we know, for example, that f is equal to pq, and these guys can be thought of as the partial with respect to x and the partial with respect to y of some function, then that means if p is fx and q is fy, I can take the partial with respect to y of this guy, and that would be f of xy. And I can take the partial with respect to q of this guy, with respect to x of this guy, and that's f of yx. But if our partials are continuous, this is actually equal to the other order. And so that's why you get, this is true. Right, so that works in 2 dimensions. If it's 3 dimensions, it's a little bit more complicated. So if this is true, then this is true, assuming that the first order partial derivatives are continuous. That's basically the sketch of the proof. But if this is true, what does that tell us about this guy?
Which one?
Green's theorem, the equation in Green's theorem.
It's just a constant.
It should be equal to 0.
It's 0. So in that case,
Professor, wait.
well, this equation you should know already. This is Green's theorem.
Wait.
So in the event that f is conservative, this equation is true, which of course that means that qx minus py is just 0. And so according to Green's theorem, the work integral will output 0. I want to actually write that down because it's an important idea. So let me know when you're done copying.
Okay. Conservative.
So this holds by Perros Theorem. You spoke about that in Calc 3. It's just a theorem that talks about the order in which you take partial derivatives don't matter as long as your functions are continuous.
Okay, done.
Which we are assuming they are here. And so all this together would mean this would mean if f is conservative, then the integral of f dot dr is equal to the double integral of x minus py a, but this guy is going to be 0, so that's equal to 0. And notice that this is true for any, and that's the important part, for any closed curve, any piecewise smooth closed curve C. Right? So it's another way to look at the conservation of work principle. You can actually get to that conclusion using Green's theorem. So it's consistent with that. Right? We kind of knew this fact already based on the fundamental theorem of line integrals. This is automatically true. Green's theorem provides another way to see that. Another consequence is that Green's theorem can allow us to use a single integral to compute area. So we're used to thinking of areas in terms of double integrals, but it turns out Green's theorem tells you that a certain double integral is equivalent to a single integral. And so any of these equations can work. So A here is representing the area of D. So one way to find the area of D, you can actually take the line integral along C, and I'm still assuming that C is the boundary of D here, of x dy. You can also take the negative integral along C of y dx. You can also take 1/2 times the line integral around C of minus y dx plus x dy.
Professor?
Why is there a hat?
Because each,
Okay, go ahead.
well, okay, so let's talk about this. Do we see why this is? What about the first one? Why is that true?
Why?
You tell me. Think of this equation in terms of Green's theorem. What does that tell us?
So that would be
What would the
Q.
P and the Q
P
be?
would be 0.
P would be 0 and Q would
And
be?
Q would be x.
So my P sub y is 0 and my
0.
Q sub x is 1.
1, right.
Right? Which means the integral of x dy is just going to be equal to the double integral of 1 dA, which we know is area of D.
Okay.
Right? And a similar computation on each of these can show you. In this case, your P would be minus y. And so you, again, when you plug it into Green's theorem, you get 1 dA. In this case, each of these would give you 1, so you get 2, and so the half, you have to cancel the 2, and you get 1 dA. So it's like you just plug in this case, your P is 0, and your Q is x. In this case, your P is minus y, and your Q is 0. And in this case, your P is minus y, and your Q is x.
Professor, can you do an example for these consequences? Like, so to compute the area, either of the formula can be used, right?
Any one of them, yeah. Use one at a time. Use whichever one's easiest for you.
Can you give an example?
I didn't really want to give one. It's just an alternative formula. But let C be anything that you know the area of. What do you want it to be? Unit circle. Right? That's a piecewise smooth closed curve. I claim that the area of this circle is going to be the line integral along C of x dy, for example. So what would that actually look like? You parameterize this circle, right? Which means your x would be cosine
T, y would be sine T.
Sine T. Your dx would be minus sine T. Your dy would be cosine T.
Cosine T.
dt. And so now, and of course here your t would be 0 to 2 pi. And so if I plug that into this line integral, what would I get?
Cosine T So
Integral from
cosine
0 to pi.
cosine t
X, which is cosine t.
and then cosine t dt.
Right, so you just get cosine squared t dt. Right? And we know that we would use the half angle formula to integrate that. So 0 to 2 pi of 1 plus cosine 2t dt. That part is going to give you 0. And so here I just get 1/2 of 2 pi, which is pi, which is the area of the unit circle.
Professor?
Yes.
So for this, your x would be a I component, y would be a j component, right?
If I'm thinking of the circle as a vector curve,
No, I'm not thinking about circuit. Any equation, if you want to use any of these three, if you have a parametric curve.
No, x is representing x in the rectangular coordinate system. Y represents y in the rectangular coordinate system. You don't think of them as components. These are the generic variables for the rectangular coordinate system. When you start talking about components, you're thinking of parameters. So it's just a nice thing to know that you can actually compute area using line integrals. That's basically what I want to tell you. And that you just know basically just by plugging them directly into Green's theorem. So you can actually compute areas by using any one of these. And of course, these things are all equal. You can use a double integral or you can use one of these. You just choose whichever one is easier, right? And you might already have information about these, and so you wouldn't need to use the double integral, etc. Right? It's just an alternative method of computing area. So Green's theorem does imply that if f is conservative, the work integral is 0, and it also gives us an alternative way of computing area. Just some nice facts to know. So now we're going to move on to 13.5. We're going to introduce a couple new concepts here. But we're going to need them to talk about the other fundamental theorems that we want to discuss. So I mentioned we're doing 4 main theorems this semester in the vector calculus part. We're doing the fundamental theorem for line integrals, we're doing Green's theorem, we're doing Stokes' theorem, and we're doing the divergence theorem. And so for Stokes' theorem, I need to talk about something called the curl of a vector field. And for the divergence theorem, I need to talk about something called the divergence of a vector field. So I'm going to just define those guys for you now. So we're going to define them and talk about how we can interpret them geometrically. So curl and divergence. I'm going to give you an operation to define. I'm going to call this the del operator. And so basically, by del is equal to this thing, partial with respect to x, partial with respect to y in 2D. Now I want to note that by itself it doesn't really make sense. It's an operator. It has to operate on something. It's kind of like how when you write sine by itself, it doesn't mean anything. You have to say sine of something. This is your thing of in the same way. It's defining an operation that you have to do on something. Okay, so I'm going to be able to plug in things into this function, into this operation. So you can more think of it as a mnemonic. So let's talk about curl. Let f be a vector field PQR. These guys are functions. then we define the curl of F to be a vector function del cross product with F. So that's the notation, that's how I can write it down. Curl of F equals this operation, and I plug in F with a cross product. Okay. So let's see what this means. And that will define a vector function here, because F is a vector, and this guy is a vector, and we're taking the cross product. You guys remember?
Is this like a gradient matrix?
Come again?
Is this like a gradient matrix we're making?
Not exactly. I'll talk about what it means later on. For now, just this is the definition. I'll talk about the meaning behind it later. But it's defining a vector, not really a matrix.
Professor, what was your
It is
point?
related to the gradient, but in a special way. Yes.
What was your point of defining the delta?
So that when I say this, you know what it means.
Oh, okay.
So this will basically mean partial with respect to x, partial with respect to y, partial with respect to z,
Okay.
cross product with PQR. Right, so this is just a way to remember the formula, because the formula is kind of huge, so this is kind of a mnemonic to remember the formula. So let's actually compute that. To write this out. This means that if I take the curl of F, what I'm doing is, you guys remember how to take cross products? Put the I, J, K, you put the partial with respect to x, partial with respect to y. So you put the components of the first vector up here, put the components of the second vector down there, and then you find the determinant. So remember, you start with the I. So you block out everything in that row and that column, and they take this times this minus that times that. So this becomes the partial of r with respect to y minus the partial of q with respect to z. And that's the first component of this vector. Minus the j component, cross out everything in his row and his column, and cross multiply. So this is the partial of r with respect to x.
Why is it plus on the textbook?
Huh?
It's plus on the textbook.
It's plus if they switch this. So here it's the partial of r with respect to x minus the partial of p with respect to z. And then plus the j component, the k component. Block out everything in that row and that column. It's the partial of q with respect to x minus the partial of p with respect to y. So notice that this actually gives you a vector function, right? So it's a vector where its components are actually partial derivatives. If they write this in the other order, they would just put a plus here. They don't want to put a negative there. So comma here, qx minus py. By the way, that expression should look familiar. We'll talk about that in a bit, the z component. And so that's how we compute the curve. So let's do an example. Let f equals this vector field. So it's going to be the vector field x, y, z, comma x squared y, comma 2y cubed. Find the curl of this vector field. like a spill here in the center. So here's how we do it in practice. You're pretty much going to set this up. You can memorize this if you want, but I wouldn't care to memorize that. I just know the method for finding it. Just set up this determinant and then compute the vector.
Professor.
Yes.
So in the quiz, if you put what is the formula of curl L, what do we need to put, the down one, or? I mean, in terms of the quiz.
Any one of these three equations.
Okay, any of the three, okay.
Yeah.
Alright, okay.
So I'd rather you not put del cross F because I won't know if you know what that means.
Okay.
But I'd rather you write out one of these. Probably the last one, but you'll eventually get there by going through this. This is sort of how you always do it. It's easiest to remember this form and just kind of compute it as you go along. So here, curl F, what it would look like is that, again, you take the partial with respect to x, partial with respect to y, partial with respect to z, and you put each component. So that's my p, I'm going to put it here. That's my q, I'm going to put it here. That's my r, I'm going to put it here. So now I'm going to do that calculation. So the first component, block out the i's column and row. So I'm taking the partial with respect to y of this guy, which gives me 6y squared, minus the partial with respect to z of this guy, which is 0. And that's my first component. Now I move on to the j component, and the j component takes the negative of the result that you're going to get. So in here, you can take the partial with respect to x of this guy, which is 0, minus the partial with respect to z of this guy, which is xy, comma. And for the k component, block out everything in the k row and k column, partial with respect to x of this guy, and partial with respect to y of that guy, minus. So we can kind of simplify that a little bit. And that vector function is the curl of my function before. Again, we'll talk about what this means in a little bit, but that's how you compute it. That's what, mathematically, that's what it means. We'll talk about geometrically what it means soon. But that's how you do it. So you're given a vector field, you find the curl of the vector field by doing this. One thing to point out, you might remember this from Calc 3, but you can only take the cross products for 3D vectors, right? Because curl is a cross product, only works for 3D vector fields. So if my f was 2D, I cannot find the curl. The curl is not defined. My f was 4D, it's not defined, etc. Yeah?
Couldn't you say that, like, take a 2D vector and just say the z component is 0?
Yeah, but then you'd be working in 3 dimensions anyway.
Okay.
You can't really think of that as 2 dimensions, strictly speaking.
Professor, but you could take the determinants in 2D dimension, can't you?
Huh?
Can you take the cross
Cross product is only defined for 3 dimensions. There's no cross product for any other dimension.
Wait, but what do you do then in differential equation? Something called Wronskian or something? You take
That's
it.
not this. That's not the same thing.
So cross product and the determinants are not the same thing?
the cross product is a determinant, but it's only defined for 3 dimensions.
Oh, okay.
Remember, there's an interpretation on this. Remember, the cross product is a vector that's orthogonal to 2 vectors in the product, right? The only time that relationship works is in 3 dimensions.
3 dimensions.
In other dimensions, it's not going to work. It's not a useful thing to talk about.
Okay.
Okay? And when you're talking about Wronskians in differential equations, you're talking about solving a system of equations, and that really comes from Kramer's rule. It's not the same thing at all.
Okay.
Okay. So it can only be defined for 3-dimensional vectors, so that will be important. You need to know that curl only works in 3D. We also have a theorem here. Now, because of how it's defined, certain things work out nice when you're talking about conservative vector fields. There's a theorem here. Just want to make sure F with continuous second order partial derivatives then the curl of the gradient of this function is always going to be the 0 vector. Which ultimately what that's going to mean is that if I have a conservative vector field, the curl of that vector field is 0. That's kind of where we're going to. That's actually not that difficult to prove. So basically, I know the curl of this guy is just going to be the determinant partial with respect to x, partial with respect to y, partial with respect to z. But this just means the components are the partial with respect to x, partial with respect to y, partial with respect to z as well. So now if I try to compute a vector here what I would have is fzy minus here, fyz. Do the middle one, I would have fzx minus fxz, comma. Do the third one, I would have fyx minus fxy, and that's equal to 0, 0, 0 by Perros theorem. I just forget how to spell this guy's name. Right? Because the partials in any order will be the same if your function is continuous. So that would always give you the 0 vector, right? Regardless of which particular gradient field it is, you'll always get 0 from the curve. Which also kind of makes sense because you'll notice that the third component of the curve looks kind of like, it's exactly that expression that you have in the double integral of Green's theorem. So that guy should be 0. So at least the z component you know should be 0. Oh, what I just said is what I wanted to write down next. This means, it's an important point, if f is conservative, then the curl of f is the 0 vector. We'll use that consequence later. Not only am I going to put it into a big theorem, but it's something that we'll use later on. I'm going to put in a big theorem now, in fact. By the way, This is a kind of statement, it's a mathematical statement called an implication. It says if this is true, then that is true. The converse is just the reverse statement, saying that if this is true, then that is true. And you can only go in the other direction if you know that these guys are continuous. So I should, it won't really come up, but I should mention it. We're usually going to be dealing with very nice functions here that are continuous everywhere. We never have to worry about that. Not one of the fundamental theorems for the semester, but it's still a very important theorem. Second tier theorem. It says the following are equivalent. That's a phrase that means they are all true or all false at the same time. So in other words, if you know any one of these things, you know all the other of these things. Okay. So these are putting a lot of things that we've discussed together. One, F is conservative. So let's say you're given a vector field, you know it's conservative. Then two, that would mean, and this is something that we spoke about before, the integral f dot dr is independent of path. I mean, if you know your f is conservative and you're given some line integral over that function, it doesn't matter what path you choose between any 2 points, you will get the same work integral. We also know that this guy here equals 0 for every smooth closed curve. There are examples of functions where sometimes it gives you 0 for a bunch of closed curves, and sometimes it doesn't. But for every closed curve, the work integral will be 0 if you know your function is conservative. That's a defining characteristic. What else? Oh, well, the equations is the next thing. Split this into part A and B. If f has 2 components, then it means that partial of p with respect to x is equal to the partial p with respect to y is equal to the partial of p with respect to x. B, if f is 3-dimensional, then the curl of f must be 0. Fifth statement. Oh, this is basically the definition. That is a gradient field. i.e., there exists a scalar function f such that the vector field f is the gradient of that scalar function. It's an important theorem in this class. Every now and then I'll give you a question that will test your knowledge on this theorem, but this theorem will really be important in classes outside of this class. So we're not going to focus too much on this theorem, but it's very important. So if you move on to like electromagnetism, for example, this theorem is going to be very important to the study of electromagnetism. For example, but it's a very important thing. Knowing our vector field is conservative automatically means all of these things are true. And if you know any one of these things are true, you automatically know the other. So if you know, for example, that your work integral is independent of path, it automatically means your vector field is conservative. It automatically means it has a potential function. Automatically means any of the others. So if you know any one of these 5 things, you automatically know all 5 things. If you know any one of these 5 things is false, you automatically know that all the other 4 things are false. Right? They'll all be true or all be false at the same time. That's what it means they're equivalent. It's a very important theorem. I don't know if I'll get to the interpretations today. I'm kind of rushing to get to it, but going to define a word very suggestive of what the curl would mean. If the curl of f is the 0 vector, then f is called irrotational. So I'm just defining the word irrotational. Of course, the root word of that is rotation. So that's kind of hinting to you what the curl kind of means. It talks about how a system is rotating around a point. We'll get to that later. First, now I want to move on to divergence. So I'm going to define both of them for you, and then we'll talk about their meaning if we have time. So we talked about curl. As far as we know right now, it's just a mathematical operation. It's just del cross product with some vector field. It gives you another vector field. And if you know that the vector field gives you 0, for example, you'll know that the function you were dealing with was conservative. Divergence. Now let's this definition here. By the way, divergence can actually work in any dimension. Right, so that's one difference there. The curl has to be in 3 dimensions. You can only find a curl in 3 dimensions. Divergence, though, you can work in multiple dimensions.
This is a scalar.
Because it's a scalar. It'll kill any vector and turn it into a scalar anyway. So it's not exactly a cross product, it's something else. So let f be a vector function in any dimension. Then
Professor?
Yes.
So if so that definition is part of this theorem?
No, this is a different topic.
I mean, no, that one. If curl f is 0, then f is called irrotational. Is that part of this? Part of this 5?
No, it's a separate.
Oh, okay.
The theorem ends here.
Okay.
Okay, so these are 5 facts that you'll know that are all true or all false at the same time. This is just me defining the word irrotational.
Okay.
To say something is irrotational means the curl is 0.
Okay.
And now I'm going to define divergence. Okay, so this is another operation we can do on vector fields. So the notation is divf, div f. You can put parentheses around this if you want. And this one is actually equal to a dot product. So you're going to dot product del with the vector. So this one gives you a scalar. And you can dot product any dimensional vector, so this one is defined for any dimensions. To discuss the equivalent of curl in higher dimensions, you need a much more complicated construct. because the cross product is just a special case of something larger called a wedge product, and it can get complicated in higher dimensions. So we're not even going to look at that. But for our purposes, curl only 3 dimensions. Divergence can actually work in any one. It's defined as that. So for example, we'll usually only be working in 2 and 3 dimensions anyway. So if f is equal to PQ, then the divergence of f is going to be partial of p with respect to x plus the partial of q with respect to y. If your f is 3-dimensional, PQR, then the divergence of f is going to be the partial of p with respect to x plus the partial of q with respect to y plus the partial of r with respect to z. And it can extend beyond that. But this is how it looks like in 2 and 3 dimensions. Right? So you're pretty much taking that derivative vector, dot producting with each of them. So you're just dot producting, multiplying each of these, and then adding them together. And that's called a divergence. So let's find the divergence of that same vector field we had last time. Let f equal x, y, z, x squared y, 2y cubed. Find the divergence of that. What is it?
X more plus Y Z.
It would be YZ.
No, Y squared.
Plus x
Two Y.
So let's write it out. So you take the partial with respect to x of this guy.
And then plus x squared, and then that would be 0, no?
So this is partial with x, that's just yz.
YZ, that would be x squared, and that would be 0.
And that's 0. So that will be your divergence, right?
What
So given a vector field, its divergence is actually a scalar function.
What application does this have?
We'll get to that towards the end of the section.
This is not the same as the divergence as like equals infinity. Is that the same?
No, it's a completely
Okay.
different thing. But the names do have something to do with it. So curl you can think of as curling. It talks about the rotation of a system. Divergence is like spreading out. Talks about the spreading out of a system. So
Okay.
I'll kind of define more specifically what that means next lecture. And so that's going to be their geometric interpretation. So. As well, they have a lot more technical applications. So whenever you're doing like fluid dynamics, electromagnetism, and all that, these things come into play. It's a theorem. Where F equals PQR. PQR have continuous second order partials. then the divergence of a curl is always 0. Proof left to the reader. That one's not that difficult. Just plug in the formula for this guy, and then take the partials of each component. You realize that you'll get 0 for the answer. And here's, again, it's one of the sad facts of this class based on what we can do. But I'm going to tell you something here that we're never really going to use technically, but it's very important in other contexts. The fact that some vector fields cannot be curls. That actually has a lot of consequences elsewhere. I.e., if G is a vector field, so vector fields themselves can also have a kind of potential, a vector potential is basically the idea. And not all vector fields have potentials, vector potentials. So it turns out, given some random vector field, it's not guaranteed that it came from the curl of something else. It might come from the curl of something else, but it's not guaranteed. Let me give you an example of such a thing. Show that this vector function cannot be the curl of any other vector field, or of any vector field. It's sad, I don't think your textbook talks about vector potentials, but I'll probably talk about them a little bit next time. For some of you, it will be important. For physics majors, especially maybe electrical engineering, it's going to be super important. I guess the other engineerings, you could probably get away without knowing it, maybe. I'm not sure, but definitely physicists and electrical engineers would need to know about this kind of thing, the vector potential. Because there's something called classical electromagnetism. It's really built up on two foundational facts. There are two things that are responsible for the entire theory, and one of them is a set of facts called Maxwell's equations. And it turns out Maxwell's equations can be interpreted as a statement about vector functions that have curls that are the curls of other vector functions. And that's a whole other thing. It's not in the scope of our class, but some of you might see it later. But let's prove that this is not the curl of some other vector field. It's actually, it might sound like a complicated thing to prove, but it's actually not. All we have to do is compute its divergence. What would the divergence of this guy be?
y squared, 0, no z squared, and then x squared.
In particular, this is not always 0. So it is not a curl. Because if you take the divergence of a curl, you always get 0. So the fact that I can take the divergence of this guy and I don't get 0 means it's not a curl of some other vector field. I'm going to have to leave you guys on a slight cliffhanger until next class. Tune in next time.
Huh?
Tune in next time for the exciting conclusion. But for now, I'll leave you with one definition of a phrase. If the divergence of a vector field is the scalar 0, then the vector field is called incompressible. And again, very suggestive. It means you can't really compress it. You don't really have a lot of space to compress things in this vector field. So if you have a container of something, when you start to model the particles in this container by a vector field, and you take the divergence of that vector field, you get 0, you know that that container is pretty stuffed. You won't be able to fit any other particles into that container without catastrophic consequences. But then, okay, so next time we'll end there. Next time we'll talk about the interpretation of curl and divergence, what they actually mean. I'll probably also talk about vector potentials, even though technically it's not in your textbook. It is something that would be useful for a lot of you to know. And you'll stop there. So, who's next class? Everything up to here. So it should cover Green's theorem, because I did mention a few things about Green's theorem. So it'll be Green's theorem and curl and divergence.
So the students be 30